Hello students, welcome to part 3 of the chapter solid state. In this part we are going to see classification of crystalline solids. In the previous part we saw the classification of solids into crystalline and amorphous. Here we are going to see the classification of crystalline solids. So most of the solids we see around us are crystalline in nature, and hence the classification is of importance. We are going to see the classification. So classification that we are going to deal in this part is based on the type of intermolecular force of attraction. So we have seen that for solids, intermolecular force of attraction is maximum compared to liquids and gases. And also based on the constituent particles, the intermolecular force of attraction differs. So for a solid, its intermolecular force of attraction depends upon the constituent particles. So let's see what are they. So as the name implies, molecular solids means the constituent particles are molecules, and the intermolecular force of attraction acting between the molecules decides this part of solids, this type of solids. And for ionic solids, the intermolecular force of attraction is the ionic bond. So automatically the constituent particles will be ions. And for metallic solids, the constituent or the intermolecular force of attraction is metallic bonding, and the constituent particles will be metal atoms. And for covalent solids, or it is also named as network solids, the intermolecular force of attraction is covalent bond. So we will see one by one, and we will see the description of the entire solid classification in this part. So in molecular solids, as we have already mentioned, it is the molecule that forms the solid. Constituent particle is molecule, and among the molecules there are three different types of intermolecular force of attraction, which we have already learned in class 11. What are the three different types of intermolecular force of attraction? The first one is the weakest of them, that is London forces. So the first type of intermolecular force of attraction among the molecules, if molecules forms the solid, then it is London forces. We will see when the London forces will play in the coming slides. Little bit more interaction or more attraction, intermolecular force of attraction is for dipole-dipole interaction, and furthermore for hydrogen bonding. So in molecular interaction, intermolecular interaction among the molecular solids, there are three types. First one is London forces, the next one is dipole-dipole interaction, and third one is hydrogen bonding. So this is about the molecular solids. When it comes to the ionic solids, as I said, the constituent particles are ions, positive and negatively charged ions. So their interaction is ionic bonding or electrostatic attraction between positive and negative charge, or Coulombic charge forces. That means charged bodies attract each other, oppositely charged. So in ionic solids, the intermolecular force of attraction is electrostatic, means attraction between positive and negatively charged ions. In metallic solids, the intermolecular force of attraction is metallic bonding. So in metallic solids, intermolecular force of attraction is metallic bonding. Whereas in the case of covalent solids or network solids, the intermolecular force of attraction is covalent bonding. So we have the details of the covalent bonding will be seen in the coming slides. So we have four different types of solids. First one is molecular solids, where molecules are the constituent particles, and their interaction can be of three types. The next is ionic solids, where the ions are the intermolecular or are the constituent particles, and the ionic bonding or electrostatic bonding forms the intermolecular force of attraction in such solids. And for metallic solids, it's metal or metallic bonding that falls under this category, and for covalent solids, it's the covalent bonding that act as the intermolecular force of attraction. So we have three different types of molecular or three different types of intermolecular force of attraction molecular solids. Accordingly, we can classify molecular solids again into three. So types of molecular solids. If the molecules does not have net dipole moment, molecules does not have net dipole moment, what does this mean? We will explain the details in the next slides, but for now we will just see certain molecules like H2, Cl2, CO2, CCl4 and noble gases. These are not really molecules, but they can independently exist. So noble gases like argon, krypton, they don't have a net dipole moment. There is no net dipole moment. So the only way to attract between, so if there is one hydrogen molecule, it has to attract another hydrogen molecule. To attract hydrogen molecules, there is only one type of intermolecular of attraction for them. They are called London or dispersion forces. London forces or dispersion forces. It's named after a scientist who discovered it. So London forces or dispersion forces. Such molecules, if they form solids, they don't have polarity in it. That means there is no net dipole moment. We will explain this in the coming slide. So there is no net dipole moment for this type of molecules. They are classified as non-polar molecular solids. If the molecular solids are the constituent particles are non-polar molecules, then those solids are classified as non-polar molecular solids. Whereas in certain other molecules are polar in nature. For example, HCl. In the case of HCl or SO2 or NH3, they have a polarity in them. In such case, if one HCl is interacting with another HCl, since they have polarity, they can get attracted between each other. Such attraction is called dipole, or such interaction is called dipole-dipole interaction. So these molecules have polarity due to net dipole moment, and such molecular solids are called polar molecular solids. So in the first part, we don't have net dipole moment for these molecules, and hence they are non-polar and they are classified as non-polar. What does the term polarity means? Polarity means both ends, the ends of a molecule must be having positive and negative charges. There will be a charge difference between the ends. These molecules don't have a charge difference, hence they are non-polar, and such solids formed from these molecules are called non-polar molecular solids. On the other hand, there are molecules that is having polarity. Such molecules are called, or such solids formed from these molecules are called polar molecular solids. Yet another, there are molecules that is having highly polar bonds, that is HF bond or OH bond or NH bond. If the molecules are having such bonds, they will also have a dipole-dipole interaction, but it will be much more stronger. In such cases, it is called hydrogen bonding. Why hydrogen bonding? You can see in all the cases, hydrogen is sharing the bond between the electronegative part. Hydrogen is sharing a bond with fluorine, electronegative fluorine. Hydrogen is pairing with the electronegative oxygen. Hydrogen is pairing with nitrogen. So if such bonds are present in a molecule, automatically there will be polarity for this bond, and hence such bonds are capable of forming hydrogen bonding. So such solids are called hydrogen bonded molecular solids. We will see these cases one by one. So first we will see what is non-polar molecular solids. So as we have explained, the force or the intermolecular force of attraction in such solids is the London forces or dispersion forces. So in non-polar molecular solids, intermolecular force of attraction is London or dispersion forces. Let's look into the details. So these are the examples of such molecules. One is noble gas, which exists as an atom. The other one is a molecule that is diatomic, and both atoms belongs to the same element. So for example, in the case of hydrogen, if you consider it as a hydrogen, you can say both are hydrogen atoms and bond is between the hydrogen atom. So what happens, both are the same atoms, so the bond between, that is the pair of electron between them, will be equally shared between these two atoms. Since the bond is equally shared, there will be no charge difference between the two atoms. Hence it is called non-polar. If there is a charge difference, then it is called polar. In this case, since both are same atoms, there is no charge difference, and hence it is called non-polar. Similar is the case with carbon dioxide. Here in the center it is carbon, on the both sides it is oxygen. Oxygen is highly electronegative, and because of its electronegativity, it will pull electrons from carbon. It will get a negative charge. But at the same time, this oxygen will also pull electron, and this will also get negative charge. Both the negative charge at both ends and carbon at the center will positive charge will cancel out. So the dipole moment will cancel out each other to both the ends. So from here it is cancelling out the dipole moment from this end. So this we have already learned, so I am not going into that details. So simply we can say that though the bonds is having polarity, net molecule is not having polarity, because the bond polarity cancel out each other. Negative charge in this direction will be cancel out the negative charge in the opposite direction. So the net dipole moment will be 0. So you can say molecule is not having dipole moment. And for noble gas, it is not having a bond, and there is no dipole moment inside. There is no polarity. Dipole moment means there will be a polarity. Net polarity for the molecule, there is no net polarity. Similar is the case with carbon tetrachloride, Cl4. Carbon in the center has 3 Cl arranged tetrahedrally. Each Cl will pull away electron, but since they are specially arranged in a way that all the negative charges of the chlorine will be cancelled out each other. So this molecule is also a molecule without dipole moment. So all these molecules are having having no polarity, or they are non-polar molecules. In such cases, for non-polar molecules, if they approach between each other, if a carbon dioxide is interacting with another carbon dioxide, a carbon dioxide molecule is interacting with another carbon dioxide molecule, then the intermolecular force of attraction between the two carbon dioxide molecules will be London forces or dispersion forces. It is the weakest of the forces among the intermolecular force of attraction, and hence under the category non-polar molecular solids. Clear? What are the properties of this solid? They have very low melting point. Why? Because it is usually gas and liquid at room temperature. Since its intermolecular force of attraction is very low, they lack polarity, and hence its intermolecular force of attraction is very low. It's very difficult to solidify them. So at room temperature you will see it as gas or liquid. But if you decrease the temperature and apply some pressure, you can solidify them. And in case if you are solidify them, then those solids will be soft. Soft means if you just try to heat it, it will very easily break. It can be easily compressed, or it can be easily bent, properties like that renders its soft property. It's having very low melting point, very low melting point. And since there is no electrons or ions involved in this, whereas there are the electrons are not loose, and for these molecules, and there are no ions involved, and hence they are non-conductors of electricity. So these are the properties of non-polar molecular solids. So in the next is the next part of the next type of molecular solids, that is polar molecular solids. So in polar molecular solids, the intermolecular force of attraction is dipole-dipole interaction. We will see what is dipole-dipole interaction. So these are the examples of the molecules that is having dipole moment. And if the solids is having such type of molecules, then there will be a dipole-dipole interaction. For example, in the case of HCl, here the bond is shared between the two type of atoms, which is their electronegativity is different. Chlorine is having higher electronegativity than hydrogen, and because of that, this shared pair of electron, or the pair of electron in this bond, is more or will move more closer to chlorine. Because of its high electronegativity, it will pull that pair of electron towards it, giving it a small negative charge, whereas hydrogen will get a positive charge. So in HCl, chlorine being highly electronegative will pull electrons towards it, giving it a negative charge, and hydrogen will get a positive charge. So if two such molecules come to close to each other, the molecules, one molecule with its negative charge will attract the positive charge of the other molecule. Again, if a molecule is having polarity, that is one end is positive and the other one end is negative, molecule with the positive end will attract the other molecule with the negative end. Thus, such an interaction is called dipole-dipole interaction, because due to this polarity, a dipole will be developed on this molecule. The details is in class 11 chapter. So because of this dipole, it can attract, or it can make a bond between the other or with the other molecule. Such an interaction is called dipole-dipole interaction. Similar is the case with SO2. SO2 is a molecule that is having a net dipole moment, and hence it can interact with other SO2 using dipole-dipole interaction. And same is the case with ammonia. So in the case of ammonia, though sometimes it can be classified as a hydrogen bonded, but because of its properties, similarity in properties to the polar molecular solids, ammonia is considered as a polar molecular solid. Again, nitrogen in the center, and hydrogen, because of its high electronegativity, it will pull electrons towards it, making it negative and the hydrogen positively charged. This creates a net dipole moment. Also, a lone pair of electron is present here, both in sulfur and in ammonia. They will also play a role. So the details you can see in class 11. Molecules with dipole moment. All these molecules are having polarity and have dipole moment, and their interaction is dipole-dipole interaction, and the molecules are called polar molecular solids. And what is their properties? They have low melting point, like non-polar. In case of non-polar, it is very low, but in the case of polar molecular solids, it's low. And usually they are gas or liquid at room temperature. They are again soft solids and non-conductors of electricity. So these are the properties of polar molecular solids, very much similar to the non-polar. But if you compare the intermolecular force of attraction or the melting point, melting point reflects the intermolecular force of attraction. Higher the melting point, higher will be the intermolecular force of attraction. Lower the melting point, lower will be the intermolecular force of attraction, or the molecule's stability, or not molecule stability, the solid's stability. Solid is more stable if the intermolecular force of attraction is higher, less stable if the intermolecular force of attraction is lower. So since this is low melting point, that means that their intermolecular force of attraction is weaker. In the case of non-polar molecular solids, it is still weaker, so that's why its melting point is very low. Whereas in the case of polar molecular solids, it is comparatively more intermolecular force of attraction, so it is low melting point. Next class of molecular solids is hydrogen bonded molecular solids. The famous example of water. Water is the basic example for the molecules that form hydrogen bonds between the molecules. Solid means ice. Apart from water, the molecules, the compounds like alcohols having OH bond, then the acids, oxalic acid, carboxylic acids, they can also form hydrogen bonding. All these are examples. So alcohols and water forms the primary examples for hydrogen bonded molecular solids. So molecules with hydrogen bonding, those molecules that is having HF bond, HO bond, HN bond, these all molecules will show hydrogen bonding, and such solids are called hydrogen bonded molecular solids. And their properties are, they have a low melting point. Generally they are liquids or solids. If they are liquids, they are generally volatile, like water is volatile, and alcohol is much more volatile than liquids. Volatility, higher volatility means lesser the intermolecular force of attraction. Here low melting point, which means that again the intermolecular force of attraction is weak. Anyway, it is better than the dipole or the polar molecular solids and non-polar molecular solids. So far we have seen three types of molecular solids. The first one is the non-polar, second one is polar, and third one is hydrogen bonded. In non-polar we have molecules that is having no polarity or dipole moment, and in the second one, in polar, we have molecules with polarity or net dipole moment. In hydrogen bond molecular solids, we have molecules that can form intermolecular hydrogen bonding. Next type of solids is ionic solids. So in ionic solids, the intermolecular force of attraction is electrostatic force of attraction, which is otherwise called as ionic or Coulombic forces. So all stands for the same type of bonding, and the bonding is between the ions. Let's look into few examples. We have given four different types of solids. First one is NaCl, and we have the ions Na plus and Cl minus. Second one is Zn2 plus and S2 minus, sulfur 2 minus. Third one is Mg2 plus and O2 minus. And the third one is Ca2 plus and F minus. So in these compounds, what have we seen here, if they are in solid form, the interaction is ionic and the interaction is between positive and negative charge. In the case of, let's see an example of sodium chloride crystal. You can see here the interaction between positive and negatively charged ions. So if you look into this particular sodium ion, it is surrounded by 4 anions. One on behind, you can see that behind also there is one, and on this side also, since it is a cross section, this side also there will be one. So each cation is surrounded by 6 other anions. Similar is the case with anion. Each anion will be surrounded with, here there is 3, one will be on the top, one is on the back and one will be on the front, so 6. So each anion and cation is surrounded by 6 other cation or anion. So ionic compounds with ionic bonding is the peculiarity of ionic solids. What are the properties? Ionic solids are hard and brittle. Brittle means breaks like a glass on heating hard. Hard means it is incompressible, it cannot be bent. If you try to bend it, it will break, and breaks like a glass. So that is brittle. It's very high melting point. So melting point, very high melting point denotes that the intermolecular force of attraction, that is electrostatic forces, is very high. That makes the solid stable. Very high melting point. And generally, since they are solid, and these negatively and positively charged ions are charge carriers, or they can conduct electricity due to these ions, but inside the solid they are not able to move. So for ionic solids, if they are in their solid form, they cannot conduct electricity. So these solids in their solid form cannot conduct electricity. But once when you are trying to lose them or trying to break these bonds, how can you break this bond? By melting them in their molten state or by dissolving them in a suitable solvent. If you break these bonds by melting them or putting them in a solution, they will start conducting electricity. So generally they are non-conductors of electricity as solids, but conducts electricity in their molten state or in solution. So again, ionic solids, its constituent particles are ions, and their intermolecular force of attraction is electrostatic force or ionic bond or Coulombic forces. They are hard and brittle. They have very high melting point, suggesting that the solid is stable, and they are non-conductors of electricity as solids. Why? Because in the solid form the ions cannot move, but if you melt them, that is allowed to flow or converted into a fluid form, or in their solution they can conduct electricity. So this is the question in the next slide. Ionic solids are insulators in their solid state, but their melt or their aqueous solution conduct electricity. Why? This is what I have explained in the previous slide. Ions have a fixed position and cannot move in solids, so that's why they cannot conduct electricity. But in their melt or in their aqueous solution, ions can freely move and conduct electricity. So in the first case, in their solid form, the ions have a fixed position, cannot move, so they cannot conduct electricity. Whereas in their melt or in their aqueous solution, they can freely move and conduct electricity. Next is metallic solids, and the intermolecular force of attraction is metallic bonding. To understand this, we have to understand what a metallic bonding is. Have taken an example, that is aluminium. If you see, aluminium has an atomic number of 13. That means 13 electron and 13 proton in the nucleus. So there is the 13 proton, and if you look into the 13 electrons, it's arranged like this. In the first shell we have 2 electrons, followed by 8 electrons in the second shell. So altogether there are 10 electrons here in the first 2 shells, and in the ultimate or in the valence shell there are 3 electrons, making the number to 13. So this valence shell is far away from the nucleus, making them or giving them some freedom to move. So these 3 valence electrons, or the valence electrons in general, you can say in the case of metals, giving its metallic bonding property. Let's see how. If you take a closer look into the metallic surface, you will see that metal atoms are arranged beautifully of aluminium. Here you will see only 2 shells with 10 electrons. The remaining 3 electrons will be flowing between the atoms. So from one atom to other, it is traveling from one atom to the other freely. It freely moves inside. This free movement will hold the atoms together. So nicely arranged, you can say that it is the metal surface, or metal is a cluster of positively charged ions that is held together by negatively charged free flowing electrons. So it is that free flowing that tends to hold the metal atoms together. So what are metals? Metals are orderly collection of positive ions. These are positive ions, and they are surrounded or held together. They are held together by a sea of free electrons that is flowing, and this gives the metallic bonding. So this is not only the case in the aluminium. I hope it's clear now what a metallic bonding is and how you can represent it. So this is not only the case of aluminium. Almost all metals it's like this. In the case of iron, copper, silver, magnesium and aluminium, in all the cases, if there is valence electron, not only it must be also unpaired electrons. So if they are unpaired electrons, they will move freely between the atoms or between the positively charged nuclei of the metal. That is the metallic bonding, and this metallic bonding is very strong. Let's see the properties. They are hard, but at the same time they are malleable and ductile. You can flatten it by heating, you can elongate it by pulling, sometimes you can bend it. So all these things comes under the two properties named as malleable and ductile. And since the free flowing electrons, there are free flowing electrons, they are good conductors of electricity. They are good conductors of electricity. And again, due to free flowing electrons, metal are good thermal conductors. How does the free flow electrons influence the thermal conductivity? So let's take this underline, for example, metallic solids. This underline, that is underline metallic solids. Consider this as an iron rod. I am heating from this end of this iron rod. You will see that after some time the heat has spread evenly on this iron rod. So if I am heating from here, that heat is received by the electrons, and since this electron can move freely through this metal, that heat is carried by these electrons to the other end of the metal. So it is because of this free flowing electrons in the metal that the heat is transferred. So due to this free electron, metals are good conductors of electricity, and metals are good thermal conductors. They have a fairly high melting point. That means that the solids are stable, and they have a metallic luster and color. All these are the attributes of free flowing electrons. So electrons excitement, which we will learn in detail in D block elements. So luster and color due to the free flowing electrons decides many of its properties. First is its hardness, its melting point, its conductivity, its thermal conductivity, luster and color, etc. So this is about metallic solids. Now into the last part, that is covalent or network solids. Intermolecular force of attraction is covalent bonding, and we have few examples that forms the covalent or network solids. First one is silicon carbide. Second is silica quartz silica, which we have already seen in the last part. Then is allotrope of carbon, that is diamond form of carbon. Then is aluminium nitride. Aluminium nitride is another example. Then the another allotrope of carbon, that is graphite form. So we have two allotropes of carbon, that is diamond, and the other one is graphite. To show few examples as images, you can see silicon carbide. You will see silicon carbon in different forms. This is just one representation, and this is the representation of silicon of diamond. Quartz we have already seen. The last part, aluminum nitride, not shown here. It is white crystalline powder. Then it is graphite, which is shown here as a lubricant. You might have also seen graphite in a daily life as lead of pencil lead. It is made of graphite. So what is the properties of these solids? They are hard solid. All these are hard solid except for graphite. Graphite is soft. So all the covalent and network solids that we come across are hard solids except for graphite. we will study the details of this exception. Again, they are all insulate except graphite. Graphite is a good conductor, though it is a network or covalent solid. Unlike other covalent or network solids, they have exemption. That is, graphite is having exemption. Generally, they have very high melting point. Very high melting point. So, we have covalent or network solids. They are hard solid except for graphite. They are insulators except for graphite. Graphite is a conductor and very high melting point. So we have seen exception here for graphite. Why is it so? So for understanding that, we will look into the two allotropes of diamond. Diamond is a true covalent solid, whereas graphite is not. We will see why by looking into the two. So we are going to see diamond, which is an allotrope of carbon. So we are going to see carbon inside diamond, then we will see the carbon inside graphite. So carbon, as we know, in the ground state has an electronic configuration of 2s2 2p2, 2s2 2p2, and its excited state, one electron from 2s will move into the vacant 2p orbital, and thus 4 orbitals are half filled. 2s and 3 2p orbitals are half filled now. In the case of diamond, for carbon, all the orbitals take part in hybridization. So all the orbitals 1s and 3p take part in hybridization. It's called sp3 hybridization. So all the orbitals will take part in hybridization. Resulting hybridization is called sp3 because 1s and 3p are there. So it is sp3 hybridization. So all of them will take part, and the resulting orbitals will be having the same energy. All the sp3 hybridized orbitals will having the same energy. If there are 4 orbitals, how will they orient in space? They will tetrahedrally orient around carbon atom. So we have carbon atom in the center, and it will be oriented in 4 different directions, that is equally spaced, that is tetrahedral structure. And to each electron or to each orbital, one carbon atom will come and bond with each, and each carbon atom will do the same, is sp3 hybridized, and will follow the network like this. Every carbon atom is sp3 hybridized, and they will form a network like this, and hence it is the named network solids. So it forms a network. This goes on like this. I have just shown few, but it goes on like this network, and the network is formed by covalent bonds. So it is named as covalent solid or network solid. So this is the case of diamond, and diamond behaves like all other covalent solids or network solids. Why graphite is not like that? We are going to see that. Why graphite an exceptional covalent solid? So we have to see again the dimensional or structural aspects of carbon. Carbon in graphite, like in diamond, it has a ground state, then it has the excited state. But unlike in diamond, here hybridization is different. In diamond it was sp3, but in graphite it is sp2. That means only 1s and 2p will take part in hybridization. 1p that does not take part in hybridization remains as p. So we have 3 sp2 orbitals and 1 p orbital. 3 sp2 orbital, these orbitals will take part in bonding, whereas this will not take part in bonding. Again, I am repeating, this is very important. We have hybridization, that is sp2, that means 1s and 2p, whereas one remaining p will remain left outside as p itself with 1 electron. All these 3 sp2 hybrid orbitals will bond with other 3 carbon atoms. Let's see. We have one carbon atom with 3 sp2. Since there is only 3 orbitals, the shape will be trigonal planar. That means a trigonal shape in a plane. If you are considering your tabletop as a plane, then all the bonds will be in the plane, and these bonds will be attached to all these bonds will be shared with 3 different carbon atoms that are also in sp2 hybridized. So you can see all this bond is shared between other carbon atom. It is also sp2, this is also sp2, like that it goes and forms a network like this. Now you can see it as a layer, a planar layer in one plane. This is a layer in one plane. So this is a layer. There will be another layer forming like this in another plane, a similar plane, again another, and several such layers lie one over the other. This is the peculiarity of graphite. What is the basic difference? Difference is the hybridization. In diamond it is sp3, whereas in graphite it is sp2 hybridized. So they form different layers. What about this electron here? The unused electron or unpaired electron. This free electron lies in between the layers like this. So they are free to move between the layers. The electron that is not taking part in hybridization is free, and that will move in between the layers. So it is the layered structure and these free electrons that making graphite unique. Still it is a covalent and network solid. Why? Because it has that network, it has that covalent bond, so it is classified as covalent solid. But unlike other covalent solids, it is layered and it has these electrons. So this gives the exceptional properties for graphite. What are they? First one is graphite is soft solid due to the layered structure. So it is not that hard and tough, it is a soft solid because the layers can be moved one above the other. So the layers can be easily moved. Second thing is, because of that layer, because of that easy movement, it can act as a good lubricant. Due to its covalent nature, it is stable, but because of its layered nature, it can be used as a lubricant between two moving objects to reduce the friction. And it can be used in pencil lead. As you spread a pencil lead over a paper, you can see that one layer of graphite will remain on the paper. This is how the pencil lead works. So so in pencil lead as well as a good lubricant, and free electrons between the layers will give the conducting power. So the free electrons between the layers makes them good conductors of electricity. So far we have learned all the four different types of crystalline solids. First one was molecules, and their intermolecular force of attraction. We have seen three types. Then ionic solids, metallic solids, and finally the covalent and network solids. And we have also seen the exceptional properties of graphite while it is still under the covalent solids. So based on this, we have few questions to answer. The first question is to identify the solids. So the features are given, their properties are given, you must be able to identify them. What type of solid is this? We have seen four different types, and under molecular solids we have seen another three different, so you have to identify them from that. The second is ionic solids conduct electricity in molten state but not in solid state. Why? Ionic solids are insulators or non-conductors in solid state, but they conduct electricity in their molten state. You have to explain it. This I have already explained in the slides, so you have to listen that and explain this. And the third one is stability of crystal is reflected in the magnitude of melting point. I have already mentioned this. So stability of a crystal is reflected in the magnetic melting point is higher, means stability is higher. So you have to answer accordingly. Now name the intermolecular force of attraction, the molecules. We have already mentioned what type of intermolecular force of attraction is in water, in alcohol. In diethyl ether, it is a polar molecule. So what type of interaction will be there? I am hinting. You can answer from this. It is a polar molecule. Methane, it is a non-polar molecule. What type of intermolecular force of attraction is acting, and what type of solid is formed from it? So water and ethyl having same kind of intermolecular force of attraction. Diethyl ether, since the molecule is having molecule is polar, what type of interaction? Methane, a non-polar molecule, what type of interaction? Try to answer. Okay, thank you.